For our first experiment, we are going to communicate from one microcontroller to another microcontroller. And we're going to use a button. We'll connect the button to pin number 1. And we're going to connect an LED to pin number 2. And they're both going to ground here. And the LED is only going to be used to diagnose or debug the button, making sure that when I press the button, the LED turns on correctly. And when the LED is on, I know that I can make a transmission or something like that. So we're going to use these two. We're going to use the button, and when we press the button, we're going to initiate the transmission to the other microcontroller. So we're going to take the TX pin from the first microcontroller. This is going to be the microcontroller that's going to be sending information to the other microcontroller. So we'll take the TX pin from this microcontroller and we'll take it to the RX pin, which will be the receiving end. The TX pin is the talking pin, and the RX pin on this side will be the ear, like the hearing pin. It'll receive the information. We're also going to put an LED on here, on this pin. This is the port B pin 0. We'll put another LED here so we can determine whether we're getting the receiving information. So we have the port B pin 0 connected to the LED, so we can determine whether the reception was correct or the reception was successful. The pin number 15, let's go back to this pin, and the pin number 15 on the first microcontroller is the TX pin. And this is going to go to pin number 14 of the second microcontroller, which is the RX pin. So to review, we are taking the first microcontroller and we're making that the transmitting microcontroller. And we're going to transmit a code to the second microcontroller. When we hit a button, we should make the LED toggle on this microcontroller just to make sure the button works over here. But then it'll also toggle this one because we're transmitting something to the next microcontroller, and we're going to make this LED light up or go back to not lighting up, and then it'll toggle back to lighting up every time we hit the button, because the only way we'd be able to make this LED work from the transmitting would be like a button on the other on the transmitting microcontroller. And you also might wonder why we're only using one line. We're just going from the TX of the first microcontroller, this is the transmitter, and then we're going to the RX of the receiving microcontroller, because we're using this microcontroller to control this microcontroller, the receiving microcontroller. We don't need to have this microcontroller, the receiving one, for this particular experiment to transmit back anything to the transmitting microcontroller, because I guess we could, like if there's an error here and maybe the transmission was not successful, we could bring back the unsuccessful state back to the first microcontroller. In this case, we really don't need to do that, so we're just going to stick with just one wire, and we're going to control this microcontroller with this microcontroller. Let's put together the breadboard and all the wires that we need to connect everything. Here's the microcontroller. This is the configuration I usually start with. The microcontroller, I generally put it from the one pin on this breadboard down, so I'll be mostly using these pins. This is the 0 pin here, or the 1 pin. And I have the ground and VCC connected to the power rails. You'll see that there's these wires connecting all the power rails together, so I get power all the way around the breadboard. You'll also notice that I have another microcontroller on the same breadboard, or on this extended breadboard, and this will be the receiving microcontroller, and this will be the transmitting microcontroller. We'll connect the switch to the microcontroller first, since that's going to be our sort of main main input device for this microcontroller. We'll put the switch somewhere over here. So we'll start with the switch. It's just standard little push button switch. Put it between a couple tie strips. Doesn't really matter where you put it there. We're going to put the LED on this side, so we have some room there. We're going to take one of the leads to the switch. We're going to take it to ground. So we'll connect it to ground and this lead of the switch. Then we'll take the other switch, the lead, and put it to PB0, or the first pin of the microcontroller. Now we'll put on the LED. But first we're going to put on a resistor. We'll need a resistor. This is a 330 ohm resistor. We need that to make sure the LED doesn't get burned out from the current and voltage. So we use the resistor to reduce the voltage going through the LED. So I'll just put the resistor somewhere in this area between two tie strips. So I have this between 25 and 24. And then I'll take the LED, and I want to make sure that the negative side goes to the ground rail. So now we'll add the LED. The negative side would be the one with a flat side. So from this lead of the resistor on the same tie strip, take that and then put the positive side on that side, and then the negative on the negative rail. Now from the other side we're going to take the wire and connect it to the other lead of the resistor and plug it into the number 2 pin, or pin P, or port B1. Let me see, I'm going to plug it right here. So now we have the button and the LED on this microcontroller, and now we can put in the LED on this microcontroller. I'm going to put the LED in this location here. So we'll start with the resistor. Put another 330 ohm resistor. I'm going to go from 23 and 24. There. This goes across 24 and 23 tie strips. Take my LED, try to find the flat side from the ground to one of the leads of the resistor, and then the other lead of the resistor, that tie strip, we'll take it to pin number 0, or port B, pin 0, or the first pin. This microcontroller will also need some power, so we need to add power to the VCC and ground pins need to go to the power rails. The number 10 pin goes to the positive, which is VCC, and the number 11 pin goes to ground, or the minus. Okay, now we need to connect the transmit pin from this microcontroller to the receive pin of this microcontroller. As we stated in our notes, the number 15 pin in our first microcontroller, that will be the transmit, or the TX pin. So we'll just take a wire and plug that in there. That's number 15. And then we'll take it to the number 14 pin of the receiving microcontroller. So what we've done to review the circuit, we have the transmitting microcontroller, we have the receiving microcontroller, we have a button to cause the microcontroller to do something, we have an LED to know if we press the button, and we have the receiving microcontroller with an LED, and we have a line plugged from the TX location, the transmit location of the first microcontroller, and we have that line going to the receive of the destination microcontroller. We have both microcontrollers powered on the power rail. Now we need to write the program to cause this microcontroller to sense the button, to light up the LED when the button is sensed, and to send information to the receiving microcontroller to make this LED light up. Okay, let's start with our skeleton code like we usually do. We can begin by putting in some pseudocode. This is human readable remarks just to sort of make placeholders for what we want to put in. I'm gonna put in initialization code here. Let's see. And we want to initialize our LED, our button, and the communication specifications. And these specifications will be how many stop bits, if we want to use parity, and the length of our data bits. Let's put this on the next line. Okay, inside of the while loop, this is our never-ending loop. It just keeps running whatever is inside this loop over and over again as we have as we're using our chip. We want to put in check the button state, and if the button is on or pressed, light up the LED and send communication. We also want to use our debouncing as we did in the previous button programs. Let's start by putting some initialization for our button and an LED. So the LED requires the data direction register for that port and that pin to be output. So we want to use DDR-B, and we're going to use the bitwise operation of OR, and we'll put a 1 or a high in, which one did we put it in? The LED is at pin 1. Okay, and then we have an input for the button. We don't really have to put anything there, but we can do it just for the sake of it. And we're going to use the AND NOT to put a low state or an input. That's pin B0. I think I have to put pin B here. And the current state of the LED would be off. We could put in, just to initialize to make sure it's off. So let's go ahead and do that. And that would be using the AND again. AND equals and then the NOT. And that would be pin B1. Let's put these two together. So this is for the LED. Set LED pin for output. And turn off LED if it's on. And then over here we're gonna set the button to be input. With the button we wanted to add button debouncing, so let's add this just below the initialization for the button. So we had an int pressed state, so we would know if the button is pressed. We had another integer, the pressed confidence level. We'll make that equal to 0, and this is usually already default at 0, but we'll put it in anyway. And then the released. Okay, so now we have the button debouncing initialization here. We also want to set this pin B0 to high, port B, because we're plugging in the button into the ground. So it goes from ground to the pin. So the pin has to be high. I'm going to change this part because this is really not saying what it should be. Button and debouncing variables. Okay, so let's go ahead and we're not going to put in the communication UART specifications yet because I want to do it to the point where we can get the LED working, get the button working, and then put the code for the button here. So we can check, if you want to, you can check to make sure that the button works and the LED works. So let's go ahead and do that. We'll put in the check for the button first. Let's put some more pseudocode in here. If the button is pressed, do this. If the button else, because the button must not be pressed, then do this. Okay, so the do this would be lighting up the LED. and we'll put in another one here because we're going to communicate. Send data to receiving microcontroller. So let's go ahead and replace this with the actual code. If bit is clear, pin B and 0. We don't need this because we're going to put in a block of code. Let's go ahead and put in the else. So let's drag this stuff up here so we know what we're doing. And then drag this. Okay, so now we have, this is a big N, not a small n. Now we have the if-then statement, or if-else statement created, and we can put in our code in here. So while we're pressing our button, we can increase our confidence level of having that button being pressed. So we're increasing the pressed confidence level, and then while we're not pressing it, let's increase our variable for the released confidence level. Of course, when we're pressing it, we want to make sure that the released confidence level is 0, because we've stopped releasing it and we are now pressing it. So obviously it's not being released anymore, and we can zero that out. Same thing with the while we're releasing it, we can have our pressed confidence level to be 0. Okay, let's put our conditions for the released pressed confidence level. So if we're really sure that the button is pressed and we have a good confidence level, what would that be? That would be, let's say if it's greater than 100. Let's try that. So we would have all of this within that all this code within this code block. And we do the same thing with release confidence level. And if release confidence level is above 100, then we do something else. So let's go ahead and set our pressed variable in here. Pressed equals 1. But this can only really happen if press is 0 to begin with. Only if pressed is equal to 0 can we show that we actually pressed it, because we only want the LED to change if we have released the button first and then pressed it again. So let's go ahead and light up the LED. But when we press the button, we don't want it just to light up. We want to, if we press the button again, it's going to turn off. So we're going to use a toggle here, port B. And we're going to use the XOR bitwise operation. Let's see, what was it, pin B1. So every time this instruction is created, it will toggle the pin B1 on and off. We can get rid of this. Since we've pressed the button, the press confidence level is greater than 100, we want to have that go back down to 0. In the released confidence level, if it passes that test, we'll go ahead and say pressed is equal to 0, since we're obviously not pressing it and we're confident of that. And released confidence level is equal to 0 as well. So now it looks like all we have to do is send data to the receiving microcontroller, and we have to set up our communication specifications on the top. Okay, we have already put in all the information that we need to make the button and the LED work. Let's see if it actually passes the make test. Oh, actually, my make file, I've changed the make file because I'm using two different chips. I'm using the 644 and I'm using the 324P. The 324P is my transmitting microcontroller, and the 644A, actually, you don't have to state the A, but the 644 is the receiving microcontroller. So my make file, I just change this manually whenever I have to program the microcontroller. So let's save that, and let's go ahead and see if this compiles or builds. Oh, I've got a lot of errors here. Let's see, port B. Oh, that looks like it needs to be PORTB. Let's try it again. Okay, and I have an error here. Where is that? Right here it says, okay, it's because I'm missing a closing parentheses. And that's probably the same thing there. So let's try it again. Okay, pressed up. I misspelled confidence. The O is too big here. Make all. This is one of the problems with not having IntelliSense. IntelliSense is when you're typing it, it'll automatically kind of figure out what you want to put in, and it knows your variables and it knows your classes and properties. So let's try it again. Let's build. All right, we have another misspelling here. Confidence level. Make all. Okay, released another one. Huh. I like that big O. All right. Okay, that one looked like it built. So this probably would work, and I could test it. I'm not going to do that because I already know it works. I've done this before. So I'm going to put in the communication specifications, and I'm going to send the data to the receiving microcontroller. And then we can actually, after I do that, we can test the button and the LED, because when I set up the UART specifications and sending the data will not really affect anything working around it. Okay, so let's put in the first specification that we need to, or the initialization we need to do. So the first thing we'll do is set up the baud rate. And we use a register called UBRRH and UBRRL. And we put the baud rate in the high bits, the high bits of the baud rate into the UBRRH and the low bits in the UBRRL. Generally, you won't even need to use UBRRH, depending on the prescaler that you need to use. In the NewbieHack website, go to Microcontroller Tutorial and go to the UART and USART details, and you'll get all the information you need to set these parameters and the initialization. And all of this information is essentially what you would see in the data sheet, but it's a little bit more readable than the data sheet. You can see here that we're creating the baud rate. You can also look at how we're doing the calculations according to your microcontroller clock speed. So you just put your microcontroller speed here, like 1,000,000 or 8,000,000 or whatever, divided by 16 times the baud rate. And you can see it an example here using the standard 1 megahertz or 1,000,000, and you divide that by the product of 16 times the baud rate of 2400, for example, and then you subtract 1 from this answer here, and then you'd get something like 25.041667, which you can only use 25 because it only accepts an integer. The UBBR only accepts an integer. And this integer could be actually more than 255 or whatever, so you'd need to have a high and a low position to make it accept a number larger. So we would be using if we're only going to be putting in 25, then we would only need to use the UBB or UBRRL. That's misspelled. I have to update that. Also, you have the option of picking either asynchronous mode, the double speed asynchronous, or normal speed asynchronous. You also have the ability to select either synchronous or asynchronous using the UMSCL bit. And the difference between asynchronous and synchronous is asynchronous is an agreed upon speed that they don't really know what the other microcontroller speed is, but they try to, or they're set to the same speed, so they receive information at the same speed as the information is being sent. But synchronous is actually putting a wire between the two microcontrollers, so the clock is wired together, and they don't have to guess at the speed. It's always going to be the same between the two microcontrollers. And there's an explanation of the data frame here, so you can understand what goes on in the data frame, setting the bit size, and this is how you do that. You'd set the parity mode, and I've got several examples on how you do that, and all of the examples are in code. So like the data sheet will give you sort of a table, but I'm giving you an actual line of code to set that particular option. And the number of stop bits to use, you can either set it for 1 or 2 stop bits, but remember that the receiving end will never use the second stop bit. It'll always ignore the second one. And I have an example initialization, which we're going to be doing now. And then I have the transmit and the receive examples. So let's go back to the program. Since I'm using an ATmega324P, that there are two different receiving and transmitting functions in this microcontroller. So I actually have to put a number of which one I'm using, and I'm going to be using 0. If you don't have this microcontroller and you have the ATmega32, then it's just this. And wherever you see a number, 0 or 1, it'll always, all you have to do is remove that from the ATmega32 for that one to work. If you have a 324, this would be the proper code to use. So we're going to make this equal. Let's create another variable called UBRR value, and this will be equal to the 25 because I'm going to be communicating at 2400 baud. You want to make sure that you pick a number that is from the table on that the same page that I just showed you. I'm going to have a table at the end of all of the values that will give you a good percentage, a reasonable or an acceptable percentage of for communicating. You can't use anything more than a 3% error, and 25 gives you a 0.2%. Alright, so let's take this, and we're going to take the UBRR value, and we're going to take the last from the 8 to 11 bits, because it really only has 3 bits that it would need in this high portion. There's other bits in this high portion, but from the end of this, like if there's, let's see, 0B, 1, 2, 3, 4, 5, 6, 7, 8. This portion, the 3 first digits of this high are the 8 through 11 bits of the UBBR value, and the rest of these bits are other bits that do other functions or set some control. Okay, so let's see, and then this one would just equal the UBRR value, and that's we don't need to put parentheses around that. But what we want to do is I'm going to introduce another way of sort of casting another type. And if I put a type here like integer or string or unsigned integer, I'm actually converting whatever is in here to this value, to this type. If this is let's say an integer, I can bring this down to, which it is actually. Let me make it an integer here. This would be, I want to convert it to an unsigned character. And unsigned just means that it won't go into the negative region. So car is an 8-bit type, and we're taking something that is a much higher than 8-bit type and we're bringing it down to 8 bits because we're not using any more of that anyway. So let's do this with this as well. So this is all you have to do to set up the baud rate. We're going to be running at 2400 baud. Okay. Now let's go on to the next one, which is we need to enable the receiver and transmitter. We really don't need to enable the receiver, but just for practice, I'm going to go ahead and enable the receiver. We're not going to be using the RX pin anyway for this example, for anything else. So let's go ahead and that one is the UCS RB, and this is essentially the control register for the UART, and we're gonna set the bits high for the receiving enable, and then we're also going to be setting it high for the transmit enable. Now this would be acceptable for an ATmega32, but in mine, since I have more than one receive and transmit features, I'm going to have to put a 0 before the B here, and then zeros after the RxEN and after the TxEN. But if you have the ATmega32, strict 32, then don't use these numbers here, because you only have one set of receive and transmit functions. So now we want to set the stop bits and the data bit length. We want to use 8 bits for data, for the data bits. We want to be able to send a a data frame with 8 bits of actual data. So we're going to use the control register C, and with my chip I have to put a 0 here because this is the first one. And let's go to the page to see what we need to do with the stop bits, which one we want to do. I'm going to go ahead and use 2 stop bits because that gives me a little bit of room between this data frame and maybe a next one that I'll be using. So where would that be? The data bit size. Let's do the stop bits first. So the stop bits bit is the USBS, and of course we're using the UCSRC. And if I want 2 stop bits, I'll just use this. So I'm just going to do a copy and paste. And now let's go and do the bit length at 8 bits. Let's go back to that page. And number of data bits. We'll use the 8-bit data length. We can use I have 2 versions of the way you can do this, and I explain a little bit on why or how that works over here. So you should take a look at that. I'm going to use this way of setting it. Okay, so now we have set the baud rate with these 2 lines. We've enabled the receive, we've enabled the transmit, and also by enabling these transmit and receive, that means we are disabling the other function of that pin, like the RX pin and the TX pin. Those also have other functions of just inputs, input or output, and you can't use that general purpose pin anymore. It has to be used for the transmit or receive if you've enabled them. If you've disabled them, if you've set those lower to 0, then that means that you can go back to using the pins as a general purpose pin. And we've also made 2 stop bits here and 8 bits of data length. Now we need to send the data to the receiving microcontroller. Now we can put in the code for transmitting the information. So first we need to do is we need to wait until the transmitter is ready. And I'm going to use some condition statement that you may not be familiar with, and I'll explain it in a second. Okay, so what I'm saying here is the UDRE inside of the UCSRA, which is the control register for the UART, and it's the A control register. The UDRE means it's if it's ready or not, if the transmitter is ready to take information to send it out. So while the UDRE is 0, it doesn't want you to. When the UDRE is 0, it means that it is still busy, or the transmit is busy. So what it's saying is this is very similar to the way we were doing like port B, and we would use the AND equals, and this is the not symbol, and then we have our bit in here. And what we're saying here is we're using the AND bitwise operation, and we're inverting the bits. We're using the not, and we're doing the same thing in here, sort of in a way we can test the UDRE bit inside of the UCSRA register, and we're checking to make sure that while it's a 0, using the not and the AND, while it's a 0, it will not allow you to pass this until it becomes a 1. So when it becomes a 1, we can go ahead and transmit. And this method is a method of polling. We are polling the UDRE bit within the UCSRA register, and we're polling it until it tells us it is not a 0 anymore. We can go ahead and transmit. The other method would be as an interrupt, and we can do that in our next project. So let's go ahead and put in what our data needs to be. Oh, let's go back here. And I have to put in the 0 here, and then the 0 at the end, because I have the 324 ATmega. Now we can set our UDR. To send the data, we just put the data into the UDR register, and we're going to put in just a binary number. So the receiving end must receive exactly this particular binary number. So in the receiving microcontroller, we'll check for this number. If it doesn't get this number, then it will not do the assigned function that we give it. in my microcontroller, I would have to put a 0 after the UDR. Okay, and we're pretty much finished with the transmitting side. Let's see if it works. Let's do a make. Okay, alright, I got some errors here. USBS, I didn't put the 0 on the end, so we have to, for my chip, I have to have a 0. Let's try it again. And the USC 0, let's see what I did wrong with that one. That's actually the way it has it in the ATmega. It says UCSZ 0. I have to actually put another 0 on the end of that for my chip. Let's see, program. I think one of these is an O. I'm not really sure. I can't really tell. What does an O look like? It should work. Let's try it again. Make all. Yep, it works. So it looks like it builds correctly. Let's go ahead and program the transmitter and see if we actually get the correct response. The microcontroller was programmed, and if we press the button, let's see what happens. Okay, good. It looks like it works. So I want the LED to turn on as I click the button. You can see the 100 for the pressed confidence level seems to be working fine. So now let's go ahead and program the other microcontroller over here. I'm going to take this code and I'm just going to hide it within a set of remark statements. Because we don't need this anymore since we're going to be programming for another microcontroller. Bring that down. Okay, so the first thing we need to do, let's do it in pseudocode. Okay, we're going to use our main. And first we want to initialize, init the LED and use UART. And we want our while endless loop here. So what are we doing inside the endless loop? Let's see. We have to check to see if the receive buffer is empty or is the receive is ready to get data, which means that the receive buffer is full. Oh, there's a flag that that gives us this information, and it's the RXC flag, and it tells us if the receive is ready to come. It's like receiving your pizza. The pizza is ready to get out of the oven, so it's fully baked. We can go get the received data. Then we can just get the data. We want to check the data if it is what we expect. Then, if so, turn on the LED or toggle the LED. So let's go ahead and initialize the data direction for the LED, and that's on port B, and it's pin 0 this time because it's we're using it on the first pin. The last microcontroller we used that was on the second pin because the button was on the first pin. And you know, the UART is actually exactly the same as what we had before because we want both of the microcontrollers to have the same information. So I'm just going to do a copy and paste of the setup, the UART setup information. I'm going to be using UART and UART interchangeably because really they're the same things, except the UART has the extra functionality of being or having the feature of synchronous communication, and but we're not going to be using the synchronous feature on this, so it's essentially UART that we're doing. Okay, so we can come over here and let's check to see if the receive is ready to get data. So we need the while, just like we are doing with the transmit. We need to make sure the receive is ready. And we're going to use the same condition we had in the other one. The control UART control register for the A control register, and then I'm going to see while this is 0, we don't want to get the information because it's not ready yet. We had RXC, right? Yeah, the RXC, and for my microcontroller, this is going to be a 0 here, and at the end of the RXC will be a 0. Okay, we can go ahead and get rid of these two because we've done this. Now let's get the data. Let's create a variable to receive the data. and we're going to get it from the UDR. And you'll notice something very interesting, that in the previous program we used UDR to transmit the data, and we're using UDR to receive the data. That seems kind of strange, because how would we be able to do full duplex if we only have one register to deal with? You'll see that we are in fact getting it from the UDR. This has to be a 0 as well, because my 324p chip. The reason why is because UDR actually has two registers in itself. There's a write register and a read register, and there's an RX. What is it? RX. I can't remember. Let's go over to the. Yeah, let's go here and find out what that is. Okay. Yeah, it's the RXB and the TXB. And here I have some information on how that works, but what happens is when we receive data, it goes into the RXB portion of UDR, and the microcontroller is smart enough to know that it'll pull the data out of the RXB portion of UDR, and if you're transmitting, it'll transmit. It'll put the data into the TXB portion of the UDR, so you don't have to worry sort of what happens behind the scenes when that's going on. Just know that it's going to work, and you can transmit and receive at the same time, and use the transmitter and receiver in a full duplex mode. Okay, so we're getting the data. I have to initialize this, so let's do that. And I'm going to put that over here, so the variable has a scope within the main and not just within the while. So we're going to use since it's not more than an 8-bit integer, I'll use the car data type, unsigned. So the signed would be that the car would be a value of -128 to +128. When it's unsigned, it shifts that to 0 to 255. Because 128 is actually 256 divided by 2. So this is 0 to 255 unsigned, and that would be 256 possibilities. So let's make this receive data. Okay, so we've created this variable. We're using it here, and let's check the contents of that variable to see if it's what we expect. So if received data is equal to 0B11110000, that's what we are sending over, then we can turn or toggle the LED. So we'll use our XOR bitwise operation, and it's a pin B0. So if we receive that, then it'll toggle the port B. So what we would have is essentially when I click on the button, both of the LEDs should be turning on and off exactly the same way. So let's get rid of this, Let's see, let's try building it and see what we have. Okay, what is this, 192U? That's on 21. That is very strange. Well, let's try this receive date. I don't know what that 192U is, so let's find out. Maybe it has something to do with this. Receive data. Nope. I see one problem here, and I forgot to put the AND. I think that's probably what was the problem there. Okay, now the received data. It must be the I before E except after C. I'll just do a copy and paste. Control C. This is where IntelliSense really comes in handy. Okay, make all. Yep, that worked. So we can go ahead and upload this to the microcontroller and see if we get the expected functionality. Forgot one thing, and that was I have to change this to 6. I have a 644A, but this is the appropriate signature for or name for the 644A. So let me save that. Make sure it still builds. Yep. And I'm going to go ahead and okay, so I've just programmed the second chip, and if I press the button, it should communicate to the next microcontroller that data that we gave it, and to turn on the LED. So let's try it. And it works. Press it again, turns off. Press it again. So you can see that this button here that is connected to this microcontroller is controlling this other microcontroller. So let's review what we've done. We have connected two microcontrollers together using to control this microcontroller with a button, and connected this microcontroller with the TX line to the RX pin onto the receiving microcontroller, and we've installed an LED to see if we are in fact receiving the data. We've also written the program to show you how to initialize the USART or the UART functionality, the features that it has. We've looked at using an 8-bit data frame with 2 stop bits. It had no parity. We didn't need to do any checking. And we implemented the button debouncing through software. Thank you for watching. If you are following along with these experiments or producing successful projects on your own, helped by these tutorials, please let me know using the Contact Us page on the newbiehack.com website. I would like to feature these on the website to benefit and motivate others to join this creative field. Thank you.